Guten Tag alle. I am pleased to be here today and to give the first presentation. Let's talk about data quality. And spannend thema, I know what you're thinking now. Exciting? Really? But believe me, if data is the new oil, then today we are talking about the purity of the gasoline. Before we get into the content, allow me a few words about myself and what we do at the Industrial Data Lab. After all, this summit is not only meant for listening but also for networking. And as is well known, this works better when you know who you are dealing with. My name is Georg Herzwürm, and this here is, as they say, my show-off slide. I started my dissertation in 1988 at the Chair of Computer Science in Cologne, back when expert systems were the big hype. My first project was with Ford, an expert system for engine noise analysis. Sounds spectacular, doesn't it? The problem? There were hardly any sensors at the time, so the car mechanic had to explain what a worn-out V-belt sounds like. Und glauben Sie mir, das ist schwieriger zu digitalisieren, als man vielleicht denkt. Wir haben die ganze Sache in Sprachen wie Lisp und Prolog programmiert, exotisch, aber stylisch. And besides the technical problems, we mainly faced acceptance issues. Workshop customers complained during the testing phase that previously the master mechanic would come in person, and now only a young punk with a computer. In my dissertation, I expanded a classic case tool for modeling with an expert system component, so to speak, AI for software engineers, before it was cool. The system could generate an SA or SD model from the natural language of users. Later, we presented the system at CeBIT. I was young, proud, full of research spirit, and the audience asked exactly one question. Can it also be printed? That was my first crash course in reality. Sometimes worlds lie between scientific brilliance and practical relevance. After a few years in software development and consulting, I finally returned to academia, because I realized that this is exactly the bridge that interests me. How to bring research, technology, and practice together in such a way that, in the end, something emerges that people really want to use. After my dissertation, I dedicated myself to another hype topic, quality management. That was the time of the great ISO 9000 boom. Plötzlich wollte jeder ein Zertifikat und die Softwareindustrie wurde nicht verschont. I was an ISO auditor at that time, conducted CMMI assessments and developed a method for customer-oriented software product development. Im Jahr 1999 erhielt ich meine erste Anstellung an der TU Dresden. Im Jahr 2003, dann habe ich mich an die Universität Stuttgart gewandert. Und seitdem erlebe ich einen Déjà-vu nach dem anderen. Mit der KI-Welle, ich have ended up back at my very first hype. I always say, I handle IT-Hypes the way my wife handles fashion. Sie wirft nichts weg, sie lagert es ein, bis es wieder trendy ist. Und wenn du dir die Bilder auf der rechten Seite anschaust, kannst du sehen, dass trotz aller Trends eine Konstante besteht. Kooperation mit asiatischen Universitäten in the field of quality management. There, I also had the great fortune to work with real pioneers, such as Professor Rakao, the inventor of QFD, and Professor Kano, whose Kano model is still a classic of customer orientation. These two gentlemen have greatly influenced me, and if you look closely, a bit of both is also reflected in our current work on data quality. At my chair for Business Informatics, we focus our research and teaching on a central theme, how companies can create value through digital products and services. Wir entwickeln Methoden und Konzepte, um systematisch diese Wertschöpfung zu gestalten, nicht auf Bauchgefühle, sondern auf wohlfundierte Ansätze. In practice, this is often dismissed as theory, usually with the undertone, nice, but it doesn't work in reality. But that's not true. Because what we develop are theories that can be translated into methods, and these methods are precisely designed to better solve practical problems. In practice, work is often done intuitively, which can be quite creative, but rarely structured and sustainably reproducible. And that's exactly where we step in. We provide the framework on which good intuition can be combined with good systematic approaches. In other words, we turn gut feeling into a method and coincidental hits into predictable successes. Before we dive into more exciting topics like AI or data products, let's first take a brief look at the fundamentals of data quality, that is, what we actually understand by good data quality and why it is so crucial. There are a whole range of standards, frameworks, and key performance indicator systems that attempt to make data quality measurable. From ISO standards to data management frameworks to metrics like accuracy, completeness, or consistency. All these approaches are valuable because they help structure and verify the technical side of data quality. But, und dies ist entscheidend, dies ist nur eine Seite der Medaille, because the actual quality is not decided in the system, but by the user. The customer perspective, i.e., whether the data really serves the purpose, is at least equally important, often even more decisive. In quality management, the so-called gap model of customer satisfaction has become established, developed by Zeithamel and colleagues in the early 1990s. I have transferred this model to the topic of data quality in the graphic shown here. First, we need to clarify what the satisfaction of the data user or data customer actually means. The data user has expectations of the data, and these expectations arise from the purpose of use. Does he want to make operational decisions with the data or control a laser machine? These expectations are also shaped by prior experiences. For example, unstructured data are usually faulty, so better to handle with caution. Likewise, by what the data provider promises, our data are up to date and verified. This also applies if the user is not a person at all, but a machine. It also expects certain formats and structures. When using the data user perceives the quality of the data and consciously or unconsciously compares the expectation with the actual perceived quality. If this comparison results in a negative outcome, dissatisfaction arises. And because expectations vary individually, it can happen that the same data satisfies one user but causes dissatisfaction in another. Und nur wenige unzufriedene Nutzer melden ihre Unzufriedenheit proaktiv, die meisten besprechen es intern. Therefore, a data provider should regularly conduct methodologically sound customer satisfaction surveys, not just with a self-made questionnaire. Overall satisfaction, Gap 5, ultimately results from several gaps. Gap 1. Reality. The difference between the actual data situation and the expectations of data consumers. An example. The production manager expects precise sensor data. IT provides data, but with gaps or drift. Gap 2. Verständnis. Diskrepanz zwischen den Anforderungen der Geschäftseinheiten und ihrer Interpretation durch IT. Die Geschäftseinheiten meinen etwas different from what IT understands. Classic misunderstanding. What is called customer in the business unit is an account in the IT system. Gap 3, Implementation, der Unterschied zwischen Verständnis und technischer Umsetzung. Even if the understanding exists, there can be issues in implementation. For example, when data models do not exactly reflect what the business side needs. Gap 4, Kommunikation, der Unterschied zwischen kommuniziertem und tatsächlicher Datenqualität. On nice dashboards, everything is green, but users are dissatisfied. Or data timeliness was promised in real time, but that was not feasible. If it had not been promised at all, it might not have been criticized. However, the announcement raised too high expectations. Gap 5, Stakeholder Satisfaction, die Summe aller Gaps. Es bestimmt, ob der Nutzer letztendlich zufrieden oder frustriert ist. This model makes visible data quality is not purely a technical issue, but a relationship problem between expectations, perception, and communication. Let's now move on to a topic that is currently on everyone's lips: artificial intelligence and data quality. I am deliberately keeping this chapter somewhat shorter, because Fabian will elaborate on the topic in his own presentation afterwards. I just want to set the framework here and show what roles AI can play in data quality management and where traditional methods still have the lead. Current, truly well-founded scientific studies on AI and data quality are rare. This is simply due to the rapid development of AI technologies. By the time a study has gone through all review processes, the model it discusses is already outdated. So I pragmatically asked someone who should know. AI itself, in this case, ChatGPT. Of course, this is not a scientifically reliable source, but it does show quite well that AI also knows its own limitations. The table here is, so to speak, a small self-analysis by AI. As you can see, AI is particularly strong when it comes to pattern recognition, understanding context, or dynamic adaptation. That is, where large data sets, unclear structures, and learning processes are involved. But for clearly defined, simple rules or organizational topics such as responsibility or governance, humans are still unbeatable. Because AI can clean data but does not take responsibility if incorrect data leads to wrong decisions. The core message is, it's not about humans or AI, but about the right division of labor. AI for data-intensive learning-based tasks and humans for context-related responsible decisions. The work of Wang and Burden beautifully demonstrates how tasks in the field of data quality can be distributed between humans and artificial intelligence. Above, we see the syntactic level, that is the formal correctness of the data. Are the values complete, correctly typed, and do formats and structures match? These are tasks that AI systems can automate excellently, for example, through validation rules or automatic error detection. At the semantic level, that is, the meaning of the data, I can also assist, for example, in standardizing terms or recognizing that temp can mean temperature or time. But here, it becomes more challenging because language and context leave much room for interpretation. At the very bottom, in pragmatic data quality, humans are then required. This is about whether the data are truly usable for a specific purpose, that is, whether they fit the decision or application. This requires understanding the context, goals, and impacts. AI can therefore help keep data technically clean and consistent, but whether they are also appropriate, relevant, and responsible remains the responsibility of humans. Having now learned the basics of data quality, in the next section we want to look at where poor data quality actually comes from, and above all, how to close the gaps, because data quality rarely fails solely due to technology. Often problems arise from misunderstandings, unclear processes, or lack of coordination among the involved parties. Having seen how diverse the causes of poor data quality can be, the natural question arises: how do we close these gaps? Let's look at each gap. Gap 1, reality. Here, data profiling, audits, and monitoring help create transparency. Gap 2, Verständnis. Daten, Governance, Rahmenwerke, gemeinsame Glossare und Workshops helfen, ein gemeinsames Verständnis zu etablieren. Gap 3, Implementation. Modellierung von Standards, Validierungsregeln und Datenverwaltung unterstützen in diesem Bereich. Gap 4, Kommunikation. Der Lücke zwischen kommuniziertem und tatsächlichem Datenqualität existiert hier. Transparent, KPI, definitions and dashboards that honestly show problems help restore trust. And finally, Gap 5. Only those who close all gaps achieve true data quality, not just technically clean data, but also user-appropriate data. The bottom line, data quality is not purely a technical task, it is a communicative, organizational, and cultural issue. Or, to put it bluntly, you can't just clean data at the push of a button, you also have to get the relationships between the people working with it in order. The term akrasia originates from ancient Greek and means acting against better judgment. In other words, you know exactly what would be right, but you do the opposite anyway. In the context of data quality, this phenomenon is particularly evident. Teams know exactly how they could ensure good data quality, but they postpone it because short-term goals like speed, feature delivery, or cost pressure take precedence. Typical sentences heard in this context include, "I will enter the data later," "We will clean up duplicate entries after go live," or "We will do the monitoring when the system is running stably." This is not ignorance, it is the classic conflict of goals between short-term success and long-term data health. The result, over time, the organization accumulates an ever-increasing data technical debt, a kind of data mountain of debt that will eventually have to be paid off at a high cost. The reasons for this are usually the same: a preference for quick results over solid fundamentals, a false sense of security through tools and automation, lack of accountability for data integrity, and the dangerous attitude, later, which in practice almost always becomes never. Or in other words, Akrasia explains why even smart people sometimes do stupid things with data. Let's now move on to an exciting idea: data as a product. When IT provides data for specialized departments, it can certainly be considered a service, a kind of service product. Obwohl intern oder extern, mit realen Preisen oder ohne, zunächst spielt das keine Rolle. According to the modern understanding of quality management, every organization consists of a chain of internal customer-supplier relationships. Jede Abteilung ist sowohl ein Kunde als auch ein Lieferant zur gleichen Zeit. Translating this to data means IT is the supplier of a data product, and the department is the customer using this product. If this way of thinking is pursued consistently, it suddenly becomes clear that data quality is also a service quality, and that, in theory, it could also be monetized, i.e., data quality as a service, where quality is not only measured but also evaluated and billed. In short, those who provide data should do so with the same standard as a company offers its external products or services, namely customer-oriented, zuverlässig und mit einer klaren Wertversprechung. This slide shows, with a wink, the 4 possible ways to develop a data product, or to be a bit more honest, the 4 variants between success and catastrophe. At the top of the axis, you see the market orientation, the voice of the customer. The better we understand what the customer really needs, the further we move upward. On the horizontal axis lies the product development competence, the voice of the engineer. The better we are at implementation, the further we go to the right. If both are weakly developed, we end up in the bottom left. The wrong product, implemented incorrectly. A classic in IT, nobody needs it, and yet it doesn't work. If we have the right product in sight but develop poorly, then we are in the top left, the right product, but done wrong. The idea is correct, but the implementation fails due to data quality, usability, or performance. Bottom right, the wrong product, but made correctly, technically brilliant, well-modeled, high-performing, but unfortunately completely off the mark. And the goal that we all strive for is located at the top right, the right product, properly implemented. This succeeds when market and technical perspectives are in balance, when the voice of the customer and the voice of the engineer come together. This is exactly where our approach with QFD begins. It systematically connects these 2 voices so that data products are not only technically brilliant, but also customer-centric, useful and value-adding. Hier sehen Sie ein praktisches Beispiel dafür, wie das Konzept der Qualitätsfunktionseinsatz oder QFD auf das Thema Datenqualität angewendet werden kann. On the left side of the table are the customer needs, that is, what data users truly expect. Reliable data for decisions, timely availability, comprehensibility, an integrated view across systems, and trust in transparency. At the top are the requirements from the perspective of data engineers, divided into functional and non-functional requirements. Functional means what specific functions must the system provide, such as data validation, data integration, data lineage, or error notifications. Non-functional refers to quality characteristics such as accuracy, latency, completeness, traceability, or accessibility. In the middle, you see the actual QFD matrix, the so-called house of quality. The numbers 1, 3, and 9 indicate the strength of the correlation between customer needs and technical requirements. 1 means a weak correlation, 3 a medium, 9 a strong connection. When we weight this across all rows, the so-called weighted impact is derived below, that is, the influence of each requirement on overall customer satisfaction. The beauty of this method, it creates a direct link between the data user view and the data engineer view, that is, between what users need and what IT must deliver. Or in other words, QFD ensures that technical measures such as data profiling, integration, or monitoring are specifically aligned with user needs, and not just implemented because they are technically possible. In the end, this results in a data quality-oriented design based on consistency and alignment, precisely what is often missing in data-driven organizations. Before we conclude, I would like to briefly introduce some of our ongoing research projects which specifically deal with the topic of data quality. The slide shows only a selection, namely those projects where data quality plays a central role, whether in industrial applications, AI support, or in the design of data products. They provide a good overview of how diverse the topic is in research and practice, from technical aspects such as data profiling and governance, to organizational questions such as how to sustainably embed data quality within a company. At my chair, we are not only concerned with the application of QFD in the field of data quality, but also with the further development of the QFD method itself. A central question is, how can modern AI technologies help better capture and understand the voice of the customer? While traditional QFD approaches rely heavily on interviews, workshops, or surveys, today we use advanced AI techniques such as topic modeling, sentiment analysis, or entity recognition. This allows us to go beyond the surface and identify hidden customer needs and trends that often remain undiscovered in traditional VOC approaches. AI helps us process unstructured data from various digital sources, such as social media, support tickets, or online reviews, and convert it into structured, analyzable insights. Wir können dann direkt diese Erkenntnisse in QFD-Matrizen einbringen and keep them up-to-date, data-driven, and fact-oriented. The result is a significantly more dynamic, holistic, and scalable understanding of customer requirements. The illustration shows an example of an NLP pipeline, which converts raw customer feedback into structured, actionable insights. A great example of how QFD and AI can work together to make the voice of the customer louder and clearer. Machine learning projects often start with great enthusiasm, but without clear design specifications. Everyone just begins to train, test, and optimize. The problem? When the project is finished, no one remembers exactly why the model works the way it does. Reproducibility and systematic quality assurance are often left behind. To close this gap, a modified version of QFD was developed by Villanueva Zacharias within the GSA-ME doctoral program at the University of Stuttgart. This approach transfers structured thinking from quality management to the world of machine learning. The principle: it does not start with the data or the algorithm, but with domain-specific needs, that is, the actual goals or problems from practice. These are then gradually translated into MLL functionalities, software components, and quality metrics. The illustration shows the overall structure of this QFD framework for machine learning. It ensures that requirements, design decisions, and quality criteria are systematically linked, and that ultimately a model is created that is traceable, verifiable, and reproducible. Or to put it casually, QFD helps to elevate AI projects from intuition to engineering craftsmanship. A central problem of many machine learning projects is that they often start unstructured. You have a goal, data, and a model, but no clear, traceable specification. This makes it difficult to understand, verify, or even reproduce the results later. This is where the approach of structured specifications comes in. By combining matrix structures, known as QFD houses, with clearly defined content templates, a framework is created that ensures ML solutions become interpretable, traceable, and verifiable. This means teams not only document technical details but also requirements, target metrics, and quality features in a consistent form. These specifications can then be stored in a central knowledge repository so they can be reused, adapted, and continuously improved in future projects. This saves effort in designing new solutions and at the same time ensures greater consistency and quality in a company's machine learning initiatives. The illustration shows how this multi-stage QFD approach has been specifically applied to the design of ML solutions, from needs through function to quality assurance. This slide shows the results of a dissertation conducted at my chair, supervised by me, and it beautifully illustrates how to develop a viable data-based business model from an existing technology. One example of this would be data quality as a service. The starting point is not a new customer requirement, but an existing technology, a classic technology push. The challenge is to derive a clear value proposition for the customer from this technological basis. The model you see here describes the path from the technology through its functional and non-functional properties to the benefit promise. It is therefore about understanding what concrete added value does this technology provide for the customer? For example, through more reliable decisions, lower process costs, or greater transparency in the data landscape. This structured approach enables the strategic transformation of existing technologies into data-driven business models, thus combining technology with market thinking. In short, not technology for the sake of technology, but technology with a sense for the customer. Finally, I would like to give you a brief insight into the ongoing research projects at my chair. Here you see a selection of current topics, exclusively those projects that relate to data quality, data management, or data-based business models. The range extends from methodological approaches, such as the evaluation of data sets for data sharing, to data-driven prioritization in agile development processes, up to data-driven circularity, that is, the use of data to close industrial material cycles, for example in batteries and metals. The further development of QFD also plays a central role, for example, in the question of how digital products and services can be systematically designed and improved. These projects show that our focus is not only on pure technology, but also on the question, how can data and quality create real added value for companies, customers, and society? This brings me to the end of my presentation, and perhaps the most important message, because data is no longer just a byproduct of our processes, it is the product. I hope I was able to show you that data quality is not just a technical side issue, but a shared responsibility of IT, business units, and management, and that methods like QFD can help bring perspectives together.